So if you study FP1, you'll have met Leibniz's theorem, which is when you have a function f which is made up of two other functions like g and h. It's a way to derive f via this formula here. So this is my notation for deriving f n times. And you get all this, this is deriving g n k times and so on. Now this looks a bit like a mouthful, so let's just get some context around what this is actually talking about. So let's do an example. So f of x is this times this. Now, when we derive it once, we can just use product rule, right? So we can derive this one for 3x squared, leave this one alone, and then we can derive this one for 2e to the 2x and leave this one alone. And then if we wanted to do that again, we would have to do product rule again, but we'd now have four terms to create, right? Two from this one and two from this one. So let's differentiate again. Usually we'd use f dash and f double dash, but just because we might have to do this a few times, I'm just going to get used to this notation straight away. So anyway, differentiating this one gets you 6x, leave this one alone. Leave this one alone and then differentiate this again for 2e to the 2x times this by 2 and you get this. And then likewise, leave this alone. I think it's actually over there. Differentiate this one and then leave this one alone. Differentiate this one and you get this. You can bring these two middle terms together to get this, and then that helps you maybe differentiate again. You can check that I've maybe got this right, but I've differentiated all of these terms via product rule. You get 6 terms in total. You can combine some of them together if you want to, but I'm not too interested. What I am more interested in is what happens if you just generalize this to like a function made of u and v, where u and v are both functions of x. So let's do product rule once, and we end up with this u dash v plus u v dashed, and then do it again. Of course, differentiate this one, leave this one alone for u differentiated twice, v left alone, and then leave this one alone, differentiate this one, and then over here, differentiate this one, leave this one alone, leave this one alone, differentiate that one, and we can bring these two terms together and we get this. Then if we do it again, okay, we're going to create 6 things again. Differentiate via product rule here, u3v, and then u2v1, I guess will happen there. And then 2u2v1, and then 2u1v2, leaving the first alone and the second each time. And then finally here, u1v2, and then uv3. And you can combine this and this to make 3 of them, and this to make 3 of them. And what we might notice is something that is very similar to something that you will have seen before, which is you've got these coefficients 1, 3, 3, 1, and 1, 2, 1, and you've also got these powers here. If we sort of imagine these are powers for a second, which they're obviously not, but these powers are always adding up to the thing. They're always interchanging themselves and adding up to the original thing. That feels a lot like binomial expansion, right? Where you get these same coefficients, 1, 3, 3, 1, and you also have these powers kind of adding to make the original thing that you had up here. And likewise here, it's the same as a plus b squared, right? And so we extend this and we imagine what would be really amazing is if you were to differentiate this n times, this pattern would just continue, and you'd get all the choose functions in the front, just dictating what the coefficients are, and then these powers, or really these derivatives, just keep kind of swapping over and interchanging with each other and running through them. And that's what gives you this result here, right? If f of x is gh, then Leibniz's theorem says you do exactly that. You have the sum of all the binomial coefficients multiplying by these differential derivatives here, which are interchanging. So you start with 0 and then n, and then you go to 1 and n minus 1, and you go to, 1 and n minus 1, and then 2 and n minus 2, 3 and n minus 3, and so on. And you just keep doing that until you're n. And this is Leibniz's theorem, and this is what we're set out to prove in the rest of this video, because it's just a really lovely proof. It uses induction, which I'm assuming most people who are watching this are aware of, because it's in Core Pure 1. So it's something that everyone in further maths A level does. But yeah, let's go ahead and do this. And I'm just going to make this clear before I start. I am going to sacrifice quite a lot of rigor for the sake of education. 3 Blue 1 Brown has an amazing video where he's giving a lecture about the juxtaposition between mathematical rigor and the benefit and the drawbacks it has towards education. And I think it was really interesting. I'm not using the excuse, but I'm just gonna play pretty fast and loose for this, just for the sake of making a video that's actually manageable to watch. So if you do spot a mistake, I don't care. I'm just trying to get across the basic idea here. Maybe it's not 100%, but I don't care. I'm just trying to be educational here. So n equals 1. We're just going to obviously do the base case. So if we substitute n is 1, we get f derived 1 time is apparently equal to this, just putting in 1s for these things here. Now, of course, we can just do this because this is just a 2-term sum, right? So let's just put k as 0 in first, and we get this term here. And then we'll put k as 1 in, and we'll get this term here. And of course, 1 choose 0 and 1 choose 1 are both 1. G differentiated 0 times is just g. So this is actually just g h dashed, g dashed h, which is just product rule, which we know to be true. We're assuming product rule is true, by the way. Maybe I'll make another video where we actually prove that. But this proof has already fallen on its face because I'm going to use a result that I haven't proved, but I don't care. We're showing that this is true for n equals 1, and we're going to say it is because product rule holds, and so therefore we're done. By the way, you could have also done an even easier case. You could have just let n equal 0 and added up to 0. This is only a one-term thing. You just end up with g differentiated 0 times h differentiated 0 times, which is the definition of f in the first place. Of course, f not differentiated is just f. And so, yeah, it's also true for n equals 0, but this case is I think, a slightly nicer one to show anyway. Cool, so now we've done the base case, we're going to assume, that this is the assumption of step, of course, we're going to assume that it's true for some n. So we're just going to assume that this is now true. And we'll consider what happens if we try n plus 1. All right, so let's make this assumption. Let's see what happens for n plus 1. So let's consider f differentiated n plus 1 times. Now, we can't use anything to do with this because this doesn't have n plus 1 in it here. So we can't do that, but what we can do is we can say f differentiated n plus 1 times is the same as the derivative of f differentiated n times, right? To get to here, all you have to do is differentiate this one again, okay? But this, by the assumption step, I can just replace it with that. So we have this here. And now stop, because it's lemma time. So we'll get out our first lemma. I actually have a shirt upstairs somewhere that says stop lemma time on it. Because when you're doing maths, sometimes you're doing a theorem, and you just have to stop because it's lemma time. A lemma is like something that's not really worth spending a huge amount of time proving. It's just a little result that's going to be useful in the middle of our bigger result. And the first little result we're going to take advantage of is this. The derivative of some sum, that's a function of x, is the same as the sum of the derivative of f, of x. And so I'm not really going to prove this because I can't be bothered. You can do it in your own time here. I'll just give you some feeling for why it's true. If we just make f of x some really easy function like x to the k, summing from k to 0 to n maybe, we'll get something like this. Maybe I should have written in the last term, but I don't really care. So when k is 0, you just get x to 0, which is 1, then k is 1, then k is 2, and so on. And now if you derive all of this stuff, because you've done the sum first, right, and then you derive, you just get 0 plus 1 plus 2x plus 3x squared plus so on. Now, if you consider this one instead, where you have the derivative inside the sigma, you just derive x to the k, which is kx to k minus 1. And then again, from k equals 0, well, when k is 0, the first time will be 0, and then when k is 1, you get 1x to the 1 minus 1, which is just 1, and then when k is 2, you get 2x to the 2 minus 1, which is 2x to the 1, and so on. And we'll end up with the same statement. Basically, what we're saying here is writing out all the terms and then deriving them all is the same as deriving the thing you're going to use and then just writing out all the terms, which I think is kind of, I'm going to use the proof by obviousness here. Sure. So we're just going to say that's true. So I'm going to put the thing in here and we'll have this result here. Cool. Excellent. So we put this in here. Now n choose k is just a number, so I don't care about it. Let's derive this thing here. But we can derive this because we're assuming product rule to be true. So we can derive this one first to get a g differentiated k plus 1 times, because if you derive it once more, you get another one up here. And then we'll leave this one alone, and then we'll leave this one alone, and we'll derive this, and again, we'll increase this, the number of derivatives here, we'll increase it by 1 to get this here, and we'll end up with that. Now we're going to do something very straightforward, which is we're just going to say, when we've got the sum of two different things added together, we can just consider that as two separate sums. So all I've done is I've broken this sum here, and I've just said it's the sum of this bit plus the sum of that bit as well. Okay, which is nice. We know that we can do that. That's fine. So we have this here then. So what could I do now? Well, there's a couple of really cool things we can do, and this is again time for our second lemma. And we're just going to do this on this one here. But our second lemma says the sum from k equals 0 of f of k to n is the same as the sum from k plus 1 to n plus 1 of f of k minus 1. And again, when you put some thought into this, this kind of becomes obviously true. But just look at an example. So again, we'll use the same simple function. We just get this here as we said before. And now when you do it with this one, you know, the function is f of k minus 1 is just x to the k minus 1. And so when you start with k as 1, you just get 1 minus 1 is 0, x to the 0 is 1. Then you put in k as 2, and you're always one term behind, which is why you get the same thing you had here, because you are using something one further ahead. And then why do we have to go up to n plus 1? Well, because one way of thinking about it is we just need the same number of terms, right? We need the same number of terms as there were here. You could also think, well, what about the last term? If you put in k as n into this, you get x to the n minus 1. And that wasn't the last term originally. So we need to stop now n plus 1 to get the same last term. So this is true. This is equal to this. And we'll adjust this here. So we'll change that to a k equals 1. we'll change all the k's to k minus 1s, and we won't change any, and we'll change this n to an n plus 1, sorry. So that k goes to a 1, this goes to an n plus 1, and all the k's get swapped at k minus 1. So the minus 1 cancels with that plus 1. And then here, this is n minus k brackets. So n minus brackets k minus 1. The brackets expand out, and you actually end up with a plus 1 down here. This one doesn't change. I'm happy with that. So I'm going to leave that as it is. Now, what I want to do is I want to try and make these sigmas be across the same limits. Because what I've done now is I've got these g's and these h's to the same derivatives. So before they weren't to the same derivatives, which is annoying, but now they are. So I've just separated, I've just made the sigmas to different limits, but now I want to put them back in the same limits, because if I did, I could bring these g's and these k's back together because they have the same derivatives now. So the idea is, let's get rid from this, this sigma here, let's get rid of the last term. And when I say get rid of it, I don't really mean get rid of it. I just mean write it on its own down here. So when I put in, so the last term here is when I put in k as n plus 1. So let's put in n plus 1 as k into here. So n plus 1 minus 1 is just n, so that's there. And then k as n plus 1 goes there. And then when k is n plus 1, you get n minus brackets k plus 1, which makes a minus 1, which cancels that minus 1, and you just end up with 0 here. So h differentiated 0 times. And likewise over here, I'm going to get rid of the first term, k is 0. So just put zeros, this is much easier, put zeros into all of these, and you just end up with this here. So now I've just taken the last term out of this sum, and I've removed the first term out of this sum, and just wrote those on their own. Now n choose n is just 1, and n choose 0 is just 1. So that's cool, I can just get rid of those, I guess. But even more importantly, these sigmas now go over the same limits, and the g's and the h's are being derived by the same amount each time. So I can recombine these sigmas now into something that looks like this. And of course, this is a bit like saying 5x plus 4x equals brackets 5 plus 4 lots of x, right? I can just add those together, having factorized out that bit there. And we end up with this, and then these are just the terms that we removed before. So, okay, good. I'm just leaving these zeros here for sake of clarity. We'll get to that in a second. Okay, so now we need our third and final lemma of the proceedings here, which is what do we do with this object here? And this is really cool. This is my favorite bit. So we know that n choose k is defined, I guess, to be this, right? N factorial over k factorial, n minus k factorial. So we can do that to both of these, right? So this one, I mean, I'd literally just defined. And this one here, we can say is n factorial, k minus 1 factorial, because that's what's here, n minus brackets k minus 1 factorial, which is, we've seen this before, haven't we? That brackets minus minus will cancel to make it plus 1 there. So we end up with this. Now, adding fractions then, what do we need? We need the same denominator. So let's times this fraction by k over k. And the reason I've done that is because k times k minus 1 factorial is k factorial. So that's pretty cool. That's going to match with this one now. And we're going to times this fraction over here by n minus k plus 1. Because again, this red bit here is 1 more than this n minus k here. So therefore, these two terms combine together to make n minus k plus 1 factorial. And now we have the same denominators, which is excellent, because it means we can just add the numerators, keep the denominators the same. But of course, I'm going to factorize out an n factorial here and leave behind k plus n minus k plus 1. The k's cancel beautifully. You're just left with n factorial into n plus 1 factorial. Sorry, into n plus 1, which gives you, of course, n plus 1 factorial. And we end up with this here. Now, look at this really carefully, and then look at this up here. Is this not, by the way, I've just swapped this 1 with this minus k. I hope we're okay to say that I'm allowed to do that. Look at this really carefully. This is just what happens here if you replace n with n plus 1. So this here is just n plus 1, choose k. And we have this result here. Now, this is an amazing result, partly because, of course, it's going to simplify this. But even better, what we've just inadvertently proved is that Pascal's triangle does indeed create these binomial coefficients, these choose function coefficients every single time. Because look at this really carefully. This is saying, pick something in the nth row, or the nth plus 1 row, whatever, however you think about it, and then pick maybe the second and the third input. So like this one and this one. So in this row, pick the second and the third input. That's apparently equal to the next row down, third input, which is what Pascal's triangle does, doesn't it? It takes this plus this and makes this. So you pick any two inputs from the row above this one, next to each other, and you get the next rows that input there of k. So 15 plus 20 is 35. So we've just proved that this always creates choose functions, which is really cool that we did that, because that's not really often actually discussed, that this does actually work if you could bother to write it all out, which obviously you shouldn't. You should just choose functions. But anyway, I thought that was quite interesting. So we're going to combine this and this into this. So that's just what this line here says. And we're actually basically done now. We're basically done. Because if you look carefully back at these two terms that I previously removed from the sigma, I think I can just put them back in. Because this term here is just what happens when you use k is n plus 1, I believe. Because you're going to get n plus 1 there, and you're going to get n minus n plus 1 in brackets, makes a minus 1, plus 1 cancels, and you just get a 0. So I think I can put that back into the sigma and just make that an n plus 1. Of course, n plus 1 choose n plus 1 is just 1, which is also the number I've got there. And likewise here, this is just what happens when you use k as 0. So I think I can put this into the sigma and just increase this to a 0. Because again, n choose 1 plus 0 is just 1, and we've got the right coefficient here. So this is all good to go. And now look at this assumption step and the thing we were trying to prove in the first place. Fn had an n here, an n here, and an n here. Now we've got an n plus 1 here, an n plus 1 here, and I could have just swapped those over again, couldn't I, to make an n plus 1 here with a minus k. And I think this is exactly the result we need to show for n differentiated n plus 1 times. So we can therefore say this is true for f differentiated n plus 1 times. You can write the usual thing you do in induction, that we had a base case of n equals 1. We assumed it was true for any n that's integer, which I never actually said, but probably should have said for rigor, but I don't care. And then we showed that it was, if it was ever true, it's true for the next one. And therefore it's always true because we know it's true for n equals 1. But anyway, I thought that was a really, really lovely proof. It's actually a challenge question in the textbook. So if you do spot that, you can have a go at it and try recreating it next time you see it. But anyway, thanks for watching, and I'll see you next time.